as a Rocketeer, and today I interviewed the white noise team of the National Technical University of Athens. Could you please introduce yourself with your name, what you do in your team?
Yes, sure. So I'm Thanos. I'm the team leader of white noise. I'm also the propulsion lead.
Okay, I'm Victoria, and I'm developing the payload of the white noise rocket.
And I'm Evgenia, and I'm from the avionics subgroup and the communications.
How did you start your rocketry?
So the whole thing started while doing CanSATs. We participated in 3 CanSAT competitions, 2 CanSAT in Greece competition and 1 CanSAT USA, the worldwide CanSAT. What we achieved multiple prizes in the CanSATs. We won first prize in the CanSAT once in the CanSAT in Greece, a second prize again in the CanSAT in Greece, and the 4th prize at the CanSAT of USA with Daedalus, the project that we did. And then we turned to rocketry with the Kronos rocket that we're developing now, and we're going to talk about it today, and multiple other smaller solid rockets.
Basically, our team is structured in 5 subgroups. We have the propulsion team, the avionics team, the communications, the payload, the mechanical design, and everyone is working towards completing Kronos rocket.
How is it studying in your university?
In Greece, we don't have an aerospace engineering specific department. We only have other engineering schools. So we have like mechanical engineering, electrical engineering, applied physics and mathematics in the same school with other engineering schools. For example, I'm from the mechanical engineering department. So if you want to study aerospace or something so specific, basically, I would say that you can. However, you can do it through other branches like mechanical, electrical, etc. So about the English classes, we don't have a complete school that's completely in English. We have some lessons though.
Yeah.
Do you want to add something for the Erasmus and stuff?
Yeah, only when Erasmus students are in the university, some classes are in English. But other than that, the university is in Greek. And the airspace part of the Greek university, there is only one university in whole Greece that has like mechanical engineering and airspace. It's in Patsas, and it's the only one that has this specific thing.
Yeah, but it's not airspace specific. It's like a final branch to your last 2 years or so.
Yeah.
It's still the mechanical school of mechanical engineering.
Yeah, it's mechanical engineering, but it has in the name the airspace.
Yeah, something like that.
Yeah.
Do you have any plans for Erasmus?
I personally don't yet, because we have like to finish everything here with the rocketry team.
Yeah. All of us
the same. Yeah.
What are the job opportunities with your university?
Generally speaking, because we live in Greece, there are not a lot of companies that are space related, apart from LibreSpace, which is the only company that has ever put something on orbit here, which is a open source foundation. We're going to talk about it later because they are the main supporter of the rocket also. So I think for space and space related jobs, that's the only way around here to go. So maybe with some other teachers from the university too that are kind of subcontractors with the ESA, the European Space Agency, but not exactly. It's like a blurred line. So only
there's no connection between the university and the space industry. Basically, there are job opportunities in general for mechanical engineers and electrical engineers. Specifically in space, there is a lack of that in Greece.
Yeah.
Well, how did you prepare for university?
Personally speaking, I wasn't involved with rocketry specifically before going to the university. I liked space. I was a space enthusiast as far as I can remember myself. But I wasn't into rocketry because we don't actually have a rocketry community outside the university. And so I was a space enthusiast. After joining the university, I found the old white noise with the CanSATs, and I joined after joining the university.
Yeah, for high school students, there is the CanSAT competition that Thanos mentioned, which is a competition and airspace competition where rockets go 1 kilometer above ground level, and they have some mini CanSATs, that's what they call mini satellites, that execute many missions. I attended this competition in high school, but other than that, everything about rocketry began with white noise in university.
Let's clear a misconception. It's not an aerospace, because it's not space. It's 1 kilometer up.
Yeah.
So that's and the CanSATs are not satellites. They're educational things that fly.
Yeah.
So even us, when we joined the university CanSAT competitions, it's not aerospace. It's CanSAT competition. It's like something different. You're not making satellites that go on orbit, of course. anyhow, yeah.
How do you manage your team?
As mentioned before from Evgenia, we have a lot of subgroups. Each subgroup has a leader, a lead, as we call. As I mentioned, for example, I'm the propulsion lead, Victoria is the payload lead. We use a lot of different tools to manage everything. Gitlab is one of the best tools that we have, the Kanban board from Gitlab. The project is open source, so everything from Kronos can be found on our repo. We use a lot of open source tools to manage our team also. So as I mentioned, the Kanban boards from GitLab are, I think, the best tool that we have actually, because we document everything issue related in different issues. So for each project, we know exactly what's running now, what we need to run after we finish this round of issues, what is open and needs to be done like in some months, what we've done. We also keep track of our progress to the Kanban boards with the closed issues. And after that, it's really easy to make a good documentation about our project and document the whole knowledge that we have until now, because you have everything in the issues. We comment a lot in the issues and then transfer everything to the wiki page of our repo. So people are managed that way too, through the Kanban board stuff, because we know what we have to do, what everything else has to do. So if, for example, I'm in a meeting with Avionics, which is not a team that I'm actually actively involved in the design and the procedure of the avionics things, I can also see what they're doing and manage the subgroups appropriately.
Yeah, other than that, we communicate with each other through the Element platform. We do video chats through Zitzi.
Yes, it's also an open source messaging and video conference apps. Another managing tool is the meetups, of course.
Yeah.
Like we have every week, each Saturday, the general meeting, as we call it. It's about half an hour to 1 hour, I would say, which we discuss different general stuff about the team. And then we have meetings with subgroups each Saturday again, and if needed, inside the week too. Generally speaking, at the Saturday meetings, I attend every groups, and the team leads attend every group in order to have a better picture of the whole team. We also have remote members, as I remember. We have one guy from Thessaloniki. He's joining the whole development process through everything that I mentioned before.
Always using the GitLab.
Generally speaking, it's our main and best tool we could find, I think. About the full-time/part-time positions, we have both full-time and part-time positions. Each member does not give the same amount of time to the project and the team, of course. Some members have more managing, how do you call it, managing positions and stuff, not only engineering positions. So of course, we have like position titles like part-time, full-time, managers, leads and stuff.
How's the experimental rocketry and space community in your country?
I can start with this question and you can add things if you want. There are some teams that develop rockets like us. If I remember correctly, 3 or 4 teams, I would say. With us, with us included, we are 4. It's not I would not consider it a community. We don't have the bonds that rocketry teams, I think, could have in other circumstances. However, it's really small, a really small branch of students that are into rockets and aerospace in general. So the community of rocketry, it's not so big. We try to make it bigger. It's one of our goals, and accessible, because people think about rockets like it's something out of the world, which it is, and it's really difficult. And it's much difficult than developing other stuff that other groups do. However, if you have plans and dedication and take it easy, it's something that anyone can join and contribute eventually. So
also, the experimental rocketry, I think, is something that we only do right now. Most of the teams in Greece do solid rockets.
That's another difference. A big difference that
right now we're the only ones that are doing a hybrid rocket.
So more advanced propulsion systems, it's like it was something non-existent, if I'm not mistaken. Like every rocket, sounding rocket development from student branches and stuff was around solid rockets and different mixtures of solid engines. So that's what we lack again in Greece. We don't have other teams experimenting with liquid or hybrid engines and stuff. And the last one is, I think, with the certifications and stuff, that the community that we're trying to build in conjunction with Aerospace and which most of the members are the local TRA prefectures, so that we're trying to build. So it's in the beginning, I would say. Not a lot of members have certifications, I would say. So if I'm not mistaken, 3 people, 4 in Greece with L1/L2 certifications, which none of it is from a student team. We don't have either. We're trying to do a launch this summer to grab L1 and /L2 sets. So that's again a lag that we have in Greece because of the small rocketry community.
Yes, rocketry in Greece is a thing of the past 7 to 8 years.
Yeah.
Basically that. Yeah. It's really new.
Yeah, I would say less. Actually,
5 years.
How do you test and launch your rockets?
That's a sad question because it's as difficult as launching, I would say, for our project, I think, because we have even to do a static test, even to do a cold flow test of our engine requires handling difficult materials. To just do a cold flow test, that's even before the static of the engine. So we tested at the university in a football field, which is kindly given to us by the university. Mr. Spitas, Vasilis Spitas, is the headmaster of the head teacher, I would say, of the team. He's one of our mentors. He's also in the university in the lab of how do you call it, machine elements. Yeah, so he's a head teacher there, and he's helping us every way he can to find a place to test the engines.
Testing is really difficult. And
because it's really dangerous, actually.
Yeah. Also, we're doing an experimental rocket.
Yeah, everything can go boom.
Yeah.
And so the rocket is completely SRAD also. We actually design and manufacture everything.
Yeah.
So everything can go boom at any time.
Exactly.
So each test is like really difficult. So yeah. About the launch thing, do you want to add something about the test?
Technically, we're in the process of trying to find places and people to help us find a place to launch and test our parts. We have completed some tests with the university, the cold flow mainly, and we're gonna try to do more, like the static test and another cold flow. And the launch.
We're having a cold flow like next week or so, the second one.
Yeah.
So
And after that, we're gonna try to find a place to launch because also due to the high temperatures in Greece, it's really difficult to find places to
allow a fire. Yes. So, about the launch, we're doing everything we can in conjunction with LibreSpace. A lot of people from LibreSpace actually to find places to launch things legally, because right now in Greece there is no standard legal procedure to launch rockets, either they are models, high power rockets or whatever. There's not a standardized procedure. Every launch until now was done like with conjunction with the military or with the Ministry of Defense, like, okay, go launch something. So we're trying to really hard actually to find a standard procedure to do so through TRA, of course. Until now it's like another gray area that we're trying to make brighter here in Greece, in order to be able to launch everything. And we're not talking about Kronos yet, we're talking about certification rockets, because Kronos is like one of the worst rockets to launch, because it's like highly experimental, hybrid, SRAD with liquid nitrogen and whatever, like it's So we're planning to do a launch like soon, but
as soon as
possible. Yeah, that's with the rocket launches in Greece.
Would you like to join the OpenLaunchInitiative?
Yeah, well, we are in the process of checking this out because we are always looking for places to launch. And if this is something that can help us, definitely we're going to take a look at this initiative.
Yeah.
Because we were thinking the same thing.
I think that it's another thing that lacks from the rocket community, not only Greece in general, that we need to be more in contact, actually. It would be great to have like more, to know more people from other rocketry groups.
And all of us launching our rockets.
Yeah, of course, and doing a launch like with 5 or 6 rockets, like, it would be awesome. So we're into it.
How do you promote your team?
We use social media, obviously, and because we also have the Gitlab platform, everything is open source and can be found there, everything we do. So through social media, we aspire to share that kind of. We try to do events, and we attend some seminars and events, and we present our project.
Open source CubeSat workshop, one of the
in workshops that also LibreSpace and Hackerspace GR, which is our lab, creates. And in the social media, we always try to post stuff that are engineering
related.
Engineering related. We don't try to do a cluster of posts. We try to only post things that are engineering related and have something to do with the project.
We try to also promote the philosophy, as mentioned.
Obviously.
As you mentioned, because like we believe that the open source part became a fundamental part of us because of the help from the community and from the tools, from the people that we engage through it. So we feel like we need to do the same thing.
Exactly.
and other people can approach us through it. So yeah, we try to promote the same thing too.
For example, when we post something, we always put the GitLab link that says this is that thing that we made. For example, the rocket motor controller we made, the PCB. There's a GitLab link above that says here you can find everything about it.
Go and check it out basically, and contribute if you want. Like, it would be awesome.
You can find
everything.
Everything.
Do you want to join some competitions?
2 years now, we've been accepted to Spaceport America Cup. This year and the last one. However, we cancelled. We cancelled again this year because of multiple logistics and insurance errors. Because, like, in order to transport a hybrid engine rocket, like from Greece to the US, it's like really difficult. So yeah, that was one of the reasons. However, right now we're more focused on completing the rocket. Actually, I would say the competitions come like after the completion of the rocket. We're not trying to build the rocket just to go to the Spaceport America Cup or Europe or whatever. It would be a nice addition in the future.
Asset,
it would be an asset, but we're not planning to like sacrifice or compromise everything or something, even to just manage to attend like 2 months earlier competition or so. We're planning to go like next year if everything is fine and everything is good with the rocket and we successfully tested it and stuff. So yeah, very important for the community, I would say, because we've engaged multiple times with other people from different teams and the stuff. But yeah, I think it's more.
Yeah, we're more project specific. We try to focus more on the project than the competition. It's better to have a nice project, a full, complete project with everything that you want, not to compromise stuff just because the competition is nearby.
I want to give credit, however, to the Spaceport America Cup for everything that they've done for the beginning of the project. That the technical regulations that we saw there when we started the project from scratch, basically, because we wanted to do a hybrid. Sorry, we're at the Hackerspace, so yeah, we have like a bit of. It's a lab in open lab, so yeah, there are people around. Yeah, that's how we work.
Background noise.
Yeah, however, like that's the beauty of the Hackerspace. Actually, I would say we're not the only team working here, and that's great. Anyhow, I want to give the credit to a lot of the documents that we saw, because they gave us a starting point to start searching some things, and that was great for the beginning. Yeah, it helped a lot actually.
So yeah, we started thinking about the competition, and they gave us the first steps on how to start
exactly.
here.
And the technical report from other teams also helped a lot when we were beginning, because we saw teams that had like years of history and they have built like 4 or 5 hybrid rockets and stuff. They were like, okay, they did this mistake, so okay, we can avoid this mistake too. And that's the reason for the open source again, because we want people to see whatever we did wrong. So if another university wants to start a hybrid rocket engine or whatever, can actually see what we did and or even take things from us. That's the best thing I think that could happen.
We're going to say more about that in the next
sure. Okay.
What software do you use to design the engine and the rocket structure?
Multiple projects. Multiple software programs. We try to about the engine. We try to use open source tools as much as we can, like FreeCAD, OpenFOAM. We use OpenRocket for the whole rocket, of course. We started with the CAD program that we started using was Fusion 360, which is a bad habit of the past that we needed to stick around. But we try to make everything as accessible as possible. And we tend to use FreeCAD a lot, which is an open source CAD platform. And for the CAD world, I would say that's what we use. We use a lot of Octave simulation and stuff to simulate everything. We have like a complete model that we did that simulates the whole blowdown model of the nitrous oxide and the run tank and the fill system and everything, which was done in Octave. And as far, for the mechanical and engineering stuff, that's it. I talked about the FreeCAD, OpenFOAM. OpenFOAM we do also CFD, of course, and structural analysis with FreeCAD also. I think that's it from the engineering. What? OpenRocket is for the whole rocket, not for it's not a CAD software. Of course we use OpenRocket to simulate the engine. And it was a bit tricky to simulate a hybrid engine, but it was fun to do so. And you want to talk about the software that...
I actually developed the software for the payload, and we also use a lot of Octave in order to do our simulations. And we also use ROS robotics, which stands for Robotics Operating System, and Gazebo to do the simulations.
Do you plan to make a liquid-fueled rocket engine?
For now, I would say no. Right now, the engine that we have is a hybrid. It's called the Mark II rocket engine. Everyone that sees Iron Man can understand the reference, I would say, yeah. So it uses paraffin nitrous oxide, liquid nitrous oxide. It's the first engine that we actually built and tested. We have designed in the past the Mark I, which was never built completely and tested. Right now, with the Mark II, we've even did the cold flow, and we're planning to do a static like in the next month or so. So we manufacture everything. We try to manufacture everything because that was the point. And even the run tank is an aluminum tank designed by team members of the propulsion, the engine too. So about your question, we're not planning to do a liquid rocket engine because it would be like throwing away the knowledge that we have on hybrids. So it would be better to do like a bigger hybrid than to try something completely different. In my opinion, I think in the people's opinion in general. So yeah, it would be better in the next rocket or so. I think it would be a good idea to like, if Kronos works,
to continue with hybrid.
To continue with a bigger hybrid and a better design hybrid, of course. Like you cannot design the best engine, of course. So yeah, a bit tinkered and beefed up Kronos.
Do you plan to use thrust vectoring?
Kronos right now does not have any controlled surfaces or thrust vectoring, Airbrakes and stuff. Basically, I think one of the reasons that it's a really big problem is that Kronos is as complicated as it gets right now for the team. So adding things like thrust vectoring and stuff would only make it more complicated without any particular reasons right now. We needed the whole thought process of the rocket was to develop a hybrid because it's never done before, and we need to do it. And we love to do it, and it seemed to us like the middle in the mid of the difficulty scale, if you call it, from a solid to a liquid, because it has only one pressurized vessel. So yeah, it was like the mid difficulty. However, it's much more difficult than we anticipated in the beginning. So adding something like that would be awesome. Actually, there are a lot of guys that would want to do so. I would love to design a thrust vectoring system, to be honest. Yeah, or an Aerospace rocket nozzle. That would be great. But right now it's it's far out from our reach, I would say. The only controlled thing that we have is the payload, actually. Yeah, you can talk about in the next slide or so. Yeah, so the rocket does not have something like that.
What kind of fins do you use?
About the external structure, it's made from fiberglass and carbon fiber. So about the fins, we use a fin can structure. So we have the whole internal assembly of the rocket ready and bolted down. And we basically have a big tube of fiberglass, which is the upper airframe, as we call it. Then a PCS section. The PCS is a pressure control system. It's the thing between the run tank and the engine. It has like two valves, custom valves that we made with custom valve actuators. And there is the airframe there again. And the last one is the fin can, which is a fiberglass tube with wooden fins. We have a wooden core from balsa wood, like 4 millimeters or so. And then we add multiple layers of carbon fiber. We use like 7 layers of carbon fiber with a tip-to-tip layup in order to manufacture the whole fin can. So it was better for us to do a tip-to-tip layup because we found it in the end easier to do so. And yeah, we went through a phase that we wanted to have like aluminum fins in order to make them interchangeable, and with an aluminum fin can and with a base that you can slot the fins and stuff. But that was deemed unnecessary and more complicated than needed. So yeah, we just make a fin can with a lot of carbon fiber, and yeah, everything goes good, I would say. The tests went great, actually. So we have 7 layers of carbon fiber to give it the strength we need. And we also have 3 fins.
Do you have your own PCB?
Another difficulty about the rocket is that you cannot find hybrid rocket engine controllers to buy. We have what we call one of the PCBs that we developed is called the RMC, Rocket Motor Controller. Currently, we are the version 2 of this PCB, which will be the final version. So we have a bunch of sensors around the rocket. Pressure sensors, for example, we have one in the run tank, one before the injector, one inside the combustion chamber. We have like a lot of stuff. So it's a custom PCB with an STM32 on top, and it collects data from the pressure sensors and stuff, and actually decides about the launch sequence and whether we should abort or no. So we have like the ground station with a control box with a nucleo board. And when we press the initiate buttons, as I would say, a signal is sent wirelessly to the RMC through the PQ9 comms. PQ9 comms is a board developed by LibreSpace. It was used in the cubic satellites. It's actually a satellite telemetry board. So with our electronics, when developing around this board, we don't have any limit with the altitude of the rocket. Like actually, this board is made to talk to orbit, so it will surely talk like if you want to come online, if you want to put come online, for example. Yeah. Anyway, so yeah, that was actually a big plus also, and that we have the support also to do so, to develop on top of this telemetry board. Anyhow, so yeah, the RMC receives signals from the PQ9 comms to canvas, and actually decides whether we should go with the procedure of the fill, and it aborts if something doesn't look normal, like if a pressure goes more than some bar or whatever. It actually decides to abort by itself because electronics are quicker than humans. We have like the option to manually abort if needed. So, for example, the guy that sits on top of the control box can actually push a button, and then the interrupt is sent to the electronics, and it just aborts. So it depressurizes the run tank, it depressurizes the external tank if it's still during the fill procedure. So yeah, it makes the system as safe as possible to approach, basically. And the RMC also is used for the tests that we do, for the statics and controls and stuff. So it has multiple load cell channels. It has like 4 load cell channels in order to measure the thrust of the rocket and stuff. So we use it for testing also.
In general, the PCBs we made are accessible for everyone, so they're easily applicable on a lot of tests we want to use.
Actually,
also,
yes.
We have created an extended board that you can plug anything that you need.
Oh yes, the motor hub. Yeah, you're correct. I forgot about.
And currently we're creating also a data logger, which is for us to collect data, other than opening the valves and everything else.
Yeah, basically the data logger is, I would say, harder than the RMC because of its form factor. Actually, the data logger follows the PQ9 standard format. It's the standardized format that I mentioned before. It's like a board 42 by 42 millimeters, and it has like multiple altimeters, GPS, multiple IMUs. Like it's so cramped.
Yeah,
it has like 100 components or so.
Exactly, it's really small, so it's a difficult one.
Yeah, it was
and everything we create on PCBs is through KiCad, which is also an open source program, and the software is through the STM CubeID.
So we don't manufacture our PCBs ourselves. We send them to be printed, but we assemble them ourselves here in the lab at the Hackerspace.
Yeah, we create the PCBs on the KiCad. We send them to China to be printed, and they're back, and we assemble
them.
How do you transfer data from the rocket to a ground station?
I mentioned it like in the previous slide. We use the PQ9 comms, the board that I mentioned that it's developed by LibreSpace. Basically, the RMC has what we call the PQ9 stack, that we can put the comms, the data logger, and everything talks to canvas from a 9-pin connector, a small connector, and that sends data to the ground station, telemetry data also, like altitude. When we're at the launch, we can see altitude, acceleration, everything. It is sent to the ground station. We visualize the data through OpenMCT. It's a software developed by NASA JPL, which is also open source. So that's our front end. But the OpenMCT software, it only eavesdropping the data sent from the control box that we have to the rocket. It doesn't participate to the whole data exchange. So if it fails, we can still talk with the rocket. And in the control box, we have like multiple LEDs and stuff that we can see how the rocket performs, even if we completely remove the laptop that's like next to the control box. So yeah, we have what I said, the manual aborts and stuff. So yeah, that's how we transfer and track data.
Basically, all the PCBs are stuck together, and through the PQ9 comms, we get everything through the telemetry of it.
Exactly. As far as about the antennas, we actually make the antennas abroad.
Yeah. Everything is right.
Yeah, true.
Everything.
Yeah, but that's fun. Yeah, that's great.
What launch rail do you plan to use?
We need to make a custom launch rail because we needed to have attachment points for the filling system. We have a whole external fill system in order to fill the rocket's run tank, as we call it. It's the tank that's inside the rocket. So yeah, it's from we use a standardized aluminum profile that every high power rocket is lost from, but we have multiple things around it. So as it's designed now, we haven't started manufacturing yet. but it has like a detachable arm in order to remove the quick release mechanism from the rocket, which is the quick release or quick disconnect, however you want to call it, is a part of the PCS mechanism, the PCS assembly, the fittings that connect the runtime with the engine, as mentioned before, which is used to fill the runtime just before launch. So we put the rocket on the launch rail, everything, we arm the electronics, everything, everyone leaves the launch pad, and then the fill procedure begins from afar, and then the quick release disconnects, and the rocket goes flying, hopefully.
Do you play Kerbal Space Program?
So yeah, I've actually played a bit. I haven't played as much as I wanted to because I don't have time though, which is really sad. I watch a lot of live streams though. But when I'm doing work and stuff in the PC, the second monitor plays like someone that plays Kerbal Space Program because it's amazing. And it's good. Like I think KSP could be used to learn some things like point the up, flaming and down and stuff. And it's like a really good guide to see how rockets work and fly. Intro, of course, but yeah, it's better to play Kerbal Space Program than other games.
How do you recover your rocket?
We use CO2 cartridges. We, of course, have like 2 parachutes, a drogue and a main. We have a mechanism, a 3-ring release mechanism, as we call it, to separate the big main socket, basically. So the drogue pulls out the main parachute from the rocket. In order to have the first deployment, as I told, we use like CO2 cartridges. They're not pre-punctured. They're actually punctured at apogee. So a mechanism with a lead screw pushes the cartridge up to a piercer screw, punctures it, and the whole rocket at top fills with CO2 gas. That's how the payload is deployed to. And yeah, it's a custom system again. That's about the recovery.
Also, it is uploaded on GitLab, so if anyone wants to see the CAD design or anything else, they can
everything is up on the GitLab. Yeah. And the color of the parachute is, I think, pink. Basically, yeah, the whole rocket will be pink because of the fiberglass epoxy. Actually, it wasn't intended. No, I'm kidding. We were intended to paint it pink. However, yeah, the fiberglass that we use is a pre-preg fabric, and the epoxy is bright pink. It's awesome. So the whole rocket will be pink with carbon fiber black parts.
Beautiful.
Yeah, beautiful. Yeah, anyway.
Okay.
What is your payload?
Our payload is controlled at a gyro. It actually has a form factor of 1U in the stored configuration. It has a non-actuated rotor on it, so it acts as a brake in order to decrease the descent velocity. Actually, it was quite a feat to design such a rotor because the theory behind it is quite complex, and we had to fit it in a real small place. Like we had to fold it, and actually, the theory behind this is that the rotor, the radius of the rotor, is decreasing the velocity as much as a parachute of the same radius would do. So we needed to make it large, and the form factor was really difficult to fit it. However, we did a test in a wind tunnel of MTUA fluid mechanics department, and the results were very satisfactory, and we were able to achieve a really nice small descent velocity. Another cool part about the payload, like the most cool part about the payload, is that it is a controlled system. It is a robotic system. So it has 4 fins attached to its body in order to eliminate disturbances. They are actually 4 airfoils. And the mechanism behind this, the working mechanism behind this, is that an airfoil, depending on the angle of attack of the flow, generates a lift force. So we can generate lift forces and moments on the body in order to eliminate these disturbances. And the main problem with the payload, the torque of the rotor applies an equal and opposite torque on the body. So the payload, if it didn't have these fins, it would be spinning like really, really fast. So we need an automated control system in order to counteract this torque.
What was the RPM of the rotor in the wind tunnel?
The RPM, like depending on the
on the airflow, what was the max that we achieved? I don't remember. So.
The max was 1,600, I think, like up to 2,000 RPM.
Which is really fast. Yeah.
But the rotor is it has a radius, so the body with the same torque will be spinning even more faster. So we need something to counteract this torque. And it is done, like I mentioned, we do simulation in Octave, like we build a system, a model level system. In Octave, we design the PID controllers and any common filters we need because like the sensor measurements are noisy. And in order to implement that, we use ROS, which stands for Robotics Operating System. It's a very powerful tool. It's an open source tool. Like every tool we use is open source. We upload everything on GitLab, so everyone could use these. And we are able, actually, what this system is doing, the main objective of it, is to achieve a safe airdrop. Like if it were spinning, the system would become unstable and maybe it would even capsize. So the main part is to make it mechanically, the mechanical integrity of it, like the mass, the center of mass should be really low in order to make it mechanically stable, and the control system should have the appropriate gains in order to make it stable. So this is our main goal, and this is our payload.
Yeah. And it was really difficult to design because, as Victoria mentioned, we wanted it to be 1U in form factor, and everything folds, even the rotor. It was like in 2 places, and the fins go inside, and But it's really cute though. It's like
and it should be like its radius should be big, and it should extend in order to achieve all the other things.
3D printing for the win.
Do you have any big announcement or dream?
I don't think that there is a big announcement right now. A dream would be to launch Kronos, actually. To launch. But it's not a dream, it's a goal. Come on, like we're trying to do so like for 1.5 years, so we'll do it. So a dream would be like a bigger, beefier version of Kronos, I would say. Like launch Kronos successfully, learn what we need to learn, and
make it even better.
And then going crazy, and even building a big one, like.
And more robots for the payload, and
or
actuated system for the fins.
Actuating the thing, the whole thing.
Translatoring, you mentioned.
Translating with a hybrid. Like, what would be easier? So I think that's the team's goal and dream.
Could you show me your lab?
This is the back of the lab. I will turn the camera around. We work at the Hackerspace. Hackerspace, it's an open lab. It's an open source hub, I would say. Like a lot of teams work here. Actually, we work here. LibreSpace works here, making its satellites and stuff. Other individuals come here to the space to work on open source projects. The common denominator is that we share the same philosophy and ideology. So everything needs to be around it. So even though it's a bit more space-related Hackerspace, due to the fact that satellites are built here and rockets, and we have like a lot of people that don't work on rockets and stuff, so they're doing other things. That's awesome too. So that's the back of the Hackerspace. It's the electronics department, I would say. So do you want to move a bit?
Yeah.
So this is 2 of the electronics bench with spectrum analyzers and oscilloscopes and stuff. That's a load. That's a function generator. How can I say it right here? And multiple other small avionics, electronics things. A wall full of components and SMT and stuff. Actually, right back is the pick and place machine below the Firefox blanket. It's a manual pick and place. That's how we assemble the PCBs, because we have like SMT components and stuff, so we need to have a proper way to assemble everything. So we have the pick and place machine. We have 4 3D printers here. The Hackerspace has 4 3D. That's a new rack for the servers. So don't look at it. It's not finished yet. So we have like 4 3D printers. These are 2 large. That's the last one. A Delta. That 2 people from Aerospace and build. On the first one, a new resin printer. Reality, And I can look at the camera a bit more further because it's however, we can show you 20 photos for the Hackerspace, and if someone needs to see more of the Hackerspace, you can find it on the website. We will send a link for that, of course. And we also have manual machines, like we have a lathe, mills. We have 3 CNCs, a lathe CNC, a mill CNC, and a Sepogo DIY router, which we love. It's our small CNC. It actually has got a lot of parts that went to space. So that's amazing. And we have also a laser cutter that we use a lot actually. that can cut acrylics, woods.
The dust-free zone.
Yeah. Also the clean box. Yeah, we have a clean box. When satellite assemblies are done here, we use the clean box, of course, to assemble them. We also have multiple tools, and the whole hackerspace actually is run by everyone. There are some operators that we have the keys basically for the hackerspace, but it is a hub that is maintained by the people that work here in general. So with donations, with tools, with everything, it's maintained by the people that work here, whether it's us, whether it's Cyberspace, whether it's some guys that do both in Guardians and Cyberspace too, or only Hackerspace members. So yeah. And as I mentioned before, the common denominator of everything is the open source ideology. So it's open to anyone. You can just ring a bell and say, "Hi, I want to do a tour at the Hackerspace," and everyone will be happy to give you a tour of the Hackerspace.
What are your personal future plans?
That was a deep question.
Yeah. I think all of us want to go to space engineering industry.
Yeah.
Or robotics.
Or robotics, because all of us are working on a rocketry project.
I want to work in propulsion systems.
And he's the propulsion lead of Noise.
Why? Yeah. So I would love to work in propulsion systems. I would also love to work in more advanced propulsion systems, like ion thrusters and stuff. I don't know, it's so amazing. I would love to do so, like small scale satellites with tiny thrusters. I love it. So yeah, I would love to continue be a contributor at Space. So that would be a future plan for me. I would love to keep doing that. I would also love to go work at Rocket Lab. Yeah, I love Rocket Lab. If someone from Rocket Lab sees me, hi. Yeah, I love it. So yeah, I think an actual goal would to finish what we started 2 years ago, and then move forward to more advanced things. Yeah, preferably not preferably. It would be one of my goals to have the same philosophy and ideology for my next project. It's something I believe in. So
yeah, I would like also to work in a space-related robotics project, because that's the stuff that I love. Something like maybe, like what you said, actuated system, thrust vectoring things, or maybe some other stuff like Payload or anything related to space and robotics would be like a dream job.
Do you have any advice to rocketeers?
There are two important things, I would say. Being a young rocketeer myself, I would say the rocketry thing in general is run by procedures. Okay, it's not like everything in engineering basically is run by procedures. However, I think it's a bit more important. So if you are young and you want to join the rocketry community of your university or want to build the rocket yourself or whatever, follow the procedures. Follow the procedures blindly. Yeah, it's so important. I cannot stress the importance of it. Why? Because it's an expensive sport, but that's not the point. Because it's dangerous. Rocketry has to do with not explosive, with flammable stuff. They're not explosives, but it has to do with energetic devices, with fuels that contain the oxidizer, so you cannot extinguish it easily. We've seen a lot of bad things happen and dangerous things with the igniters, with rocket candy or whatever. So, for example, one thing from us that we were like, okay, it's easy. It was the igniter. It's made from rocket candy. So we're like, okay, rocket candy. What could be easier? Everyone makes rocket candy. Yeah, and we did a test in our university with the igniters, and they were burning at hundreds of degrees. And yeah, a lot of things can go wrong easily when you least expect them. So procedures. I think that the people that are in the rocket community are actually open to new members. So even us, we have student members from our team that we see it as mentoring and stuff. So yeah, we have some members that they're from high school, official members. Actually, we train them and they take part in the development of the rocket. So yeah, procedures, I would say the one. So in the procedures section comes the L1/L2 certifications. So yeah, that's important too. So yeah, one is procedures, and the second one is be cautious. Be really cautious. You need to see everything that you make like your own child, because it can blow up instantly. Be very, very cautious with everything. And space in general is something that's really specific, and every tiny part has a place, and every tiny bolt or M2 nut has a really specific place. So when you're building a model rocket that's like epoxy and carbon fins, cardboard, not carbon, which is like an RC, it's easy to build a tiny model rocket. It's better to take your time and be cautious because when you're going to build like a fin can for a 25-kilogram hybrid rocket that goes 0.88 Mach, if you have the same ideology, not ideology, like the same caution, everything is going to go better. So it's better to start because from the beginning, I would say, which is something I didn't do and I had to learn the hard way. So yeah, that's I think the two advice that I have.
What are your favorite space movies?
Interstellar.
Yeah.
Definitely.
Interstellar.
Christopher Nolan.
Space Odyssey for 2001 was nice.
Okay, yeah. I don't have a favorite. I like them. It's okay. I tend to be like, yeah, that cannot happen.
Yeah, definitely.
Yeah. You can't go near the black hole, come on. Yeah, so I tend not to enjoy it so much. I have a lot of favorite YouTubers. Though.
Yeah.
Do you want to start?
I think all of us are more into YouTube than movies.
Yeah, like my favorite one of my favorites is Colin Firth. He's not space related, but I love him. Again, Colin Firth, if you watched it, hi. Yeah, I love Colin Firth. And I also love Scott Manley. He's great. His videos are really educational, so I love watching him. BPS Space, thank you for helping us with the wet layout of the Lumineer fin can do it. If he's watching it too, thanks. X Robots.
Yeah.
I love him too.
James Bruden.
Yeah, he's great.
James Bruden.
Real Engineering is great too. Grady from how is it called? The Civil Engineer, Practical Engineering.
Lizix.
Yeah, Lizix. My God, he's helped us so with the school. Come on. Yeah, I like also Practical Engineering, but he's not like space or whatever related.
Yeah.
He's civil engineering related, but he's awesome too. How's it called? Another guy that does the renderings of cool stuff and explains it. He's done the
Lizix.
No, not Lizix. The other one with the bowling machine and the Big Ben and
Something with physics.
No. He's not with physics. I need to find his name. He's amazing.
Yeah. I would say Michael Reeves also.
Oh yes, with Scott
Yeah.
and stuff.
In Avionics, we have a thing about Phil's Lab.
Yeah, Phil's Lab also.
We always watch him.
Jared Owen.
Yeah.
I found him. Jared Owen. He's great too. And Fireball Tool also, a dude that I don't know how he's so precise with hand tools. He's amazing. But yeah, he also has a water jet load. Anyway.
Asap Science.
Yeah, Aerospace, they're great too.
As you can see, we love.
Yeah, we can keep talking for like 1 hour or so. Yeah, so let's stop it. Yes.
Do you have any questions for me?
How do you start with the whole rocket thing? How do you got into it? From KSP?
How come at your age you have started all of this?
Yeah, you managed to multiple teams in the YouTube channel to talk. That's amazing. Like,
Yeah.
props. Nice.
So I started a long time ago, such a long time ago that I don't remember when. And then I heard about this game called the Kerbal, which was about rockets. And I was like, ooh, this looks fun. And I played a lot of Kerbal. And I think I've done almost everything you can possibly do in that game. I sent a boat to Leif one time.
Nice. I would love to see it actually. I don't know if you have it on your channel. I would love to see it.
No, it's not on the YouTube channel. It's on a world which was deleted. So
Okay, same. Okay.
lost.
So what would you like to do? Like you've talked to so many rocket teams and heard so many things. What's your favorite part? Like avionics, propulsion, like aerostructures, marketing.
So my favorite part is propulsion.
Yeah.
That's nice.
And
That's
that's why I'm building rockets at home, liquid fueled rockets.
I've seen the video that you have. How do you make it? It was printed. How do you do the by propellant, whatever, a liquid one that you had a static test?
So is it like the first video that appears?
I think yes, that it's like
it's
45
the
degrees
first
or so.
Yes,
not this one. That's 3D printed PLA. I can see it. I remember another one. I think.
So this is a jet engine, a ramjet.
Sorry. How do you make the engine in general? You 3D print everything?
Yeah, so I've got some 3D printed parts. I've got some parts made with rubber tube, like the pipes, because the plastic leaks, and I've got some parts in cardboard and tape.
Yeah,
Because
God bless 3D printing. Yeah, helps so much. Like,
Yeah, I think that's the questions we have for you.
Yeah.
that's everything.
Okay, well then, bye. Yes.
Great. It was
Thank you very
nice.
much.
It was really nice
Bye.
meeting you.
Thanks for being here.
Nice. It was really nice meeting you. Thank you for taking the time.
Thank you very much.
Bye.
See ya.
Bye.
Bye.